Greetings. Today, introduction to the complexity of algorithms. I believe it's a really important topic because it's performance, how quickly your program will work, and that will impact how well do you feel about it. I think complexity is best understood through searching through data structure. So let's dive into that. Okay, it's an interview question basically, so I'll create a new class. And what we're gonna do is complexity investigation. How are we gonna do it? Method. So what the problem we will look at? Searching through a data structure. So let's select list, for instance. We have a list of data. That will be a list of integers. And the thing to do is we would like to populate it with data, and let's introduce first a constant. It will be n, number of elements in the list. 10,000. And let's comment out number of elements. And then second one, call it k, 1,000. It will be number of requests. And you'll see in a minute what I mean. Okay, so first let's populate list with random numbers. And then let's search if certain number is present in the list or no. That will be one type of a query. Second type of a query will be, let's search for maximum, minimum, and let's do the same as minimum, basically the same. Random for loop, and we will add a new element, and we next. So let's move them to input parameters. Num list size and query count. And now for each query, let's slightly rewrite. So let's add a test for it, and that will help us to see how to call it and to design the class better. Let's investigation test. And here, this one we need. Investigation and the test method. Investigation. So what we would like to do is to measure time it takes to search through such list with different options implementation. So for that, we will need probably like two methods. Seed, then in a loop, here we can put a list count. Seed will be taken. We'll take this parameter and query count. Let's add this method. Seed means we will populate the list with random data. Let's move this here as well. List. And we can have one more parameter. Let's have it for the sake of testing. It will be the maximum element with which list can be populated. Value. Great. Asks max value set to 100,000. Now we want to add searching. What we will search, or we can search for a random number as well. See if it is there. Value as variable. Okay. Let's add search. Station or stage. Let's search. Let's call the search linear, because it will have linear complexity. And how do we search? Just going for each, it should return a Boolean value. So if it's found, it's true. If it's not found, it's false. List count. If list item equals number, return true. False. And found. And just compare output. We'll see how many actual elements we find. So we populate the list with random data, and then we search, but within a limit of 100,000. So we should be able to find. Let's see. found elements, found elements plus. Okay, and we would like to measure the performance of it, so let's do Stopwatch. New. Here, output. We would like to have found elements and time is stopwatch elapsed. Good. I think we are ready to run it. Good. Let's see, 90. Time was so fast, so super quick. What if we increase the list size 100,000? And I'm thinking about increasing query count to 10,000. Let's get some seconds on the clock. Good. Almost 2 seconds. 2.9 seconds for 100,000 elements in the list, and query count 10,000. So what linear complexity means? It means that this time will scale linearly with the increase of the elements. We have list count, which is big N, linear complexity big, and if we put down 1,000, we can do an experiment. It took 2.88 seconds. Okay, let's see if it's really linear complexity. So let's increase to 200. Yeah, 4 seconds. Let's increase 2 times more. 400. Here, almost 5. 93. To be precise, what is happening? So we have actually 2 multipliers. This complexity is for each time we do a query, that's a multiplier. So it is O big from query count, and by the linear search, we iterate through each element of the list. It may return faster, kind of a random thing, but worst case scenario, it returns at the end of the list, so it has to traverse all of the elements. The average scenario, it returns in the middle of the list. We can see that right now value is 100 and the count of matches is relatively high. So in a lot of cases, it has found, almost every case, it has found an item. Let's increase this, see how it performs. So the likelihood of elements being found is far less. Yes, you can see a drastic change. Max value equals 1 million. time span was so huge. Well, let's, for the sake of experimenting, do it for 200,000 as well. Yeah, it's 200,000 now. It's 8 seconds. And let's add here. This was for max value lower. And then final test. I guess we can have it for 100,000 to have the better picture. As you can see, for the case when there are way less matches, data is much more different and it has to traverse through more of the list, we get very linear scaling. Basically, you multiply this by 2, you get 8 seconds, you multiply this by 2, you get 16 seconds within the range. So this experimentally shows us that indeed it's an O big from n linear dependency on the number of elements. That's very good experiment. I encourage you to do your own experiments with data, and next time let's see what .NET offers, like in terms of searching. Obviously, we can improve this by doing something with the data structure, especially in a case when we have initialization one time and then we do queries. Hope you enjoyed it and see you in the next one. Bye for now.